Welcome again to the MOOC program. Today we will discuss three oxidizing agents. First one is ceric ammonium nitrate, which is called CAN, then DDQ, and last is selenium dioxide, ACO2. So ceric ammonium nitrate is commercially available, and this is orange red color, used as 1 electron oxidant and also Lewis acid catalyst among the lanthanide complexes. Advantage of ceric ammonium nitrate is it is low toxicity, it is inexpensive, it is soluble in many organic solvents and also in water, it is also air stable. And cerium exists in two stable adjacent oxidation state +3 and +4. So, if you see the structure of ceric ammonium nitrate, so 6 nitrate is bringing -6 and 2 ammonia is bringing +2. So, cerium is here +4. So, what happens, it on reduction it can go to +3, another oxidation state after oxidizing. Electronic configuration of cerium in ground state is xenon 4F1 5D1 6S2. So, ceric ammonium nitrate has been used in many oxidation reaction. Mainly first we will discuss oxidation of secondary alcohols. So, here you can see the secondary alcohol is selectively oxidized to the carbonyl compound with catalytic amount of ceric ammonium nitrate and another stoichiometric oxidant sodium bromate. So, if you see the bromate structure, so this is sodium bromate, this is used as stoichiometric oxidant with catalytic amount of CAN, and these two chiral center are undisturbed in this oxidation reaction. Similarly, this hydroxyketone was oxidized to benzyl with ceric ammonium nitrate and sodium bromate 1 equivalent in acetonitrile water solvent. And this is very interesting reaction. Here one secondary alcohol and one primary alcohol is there, and under this condition ceric ammonium nitrate 10 mole%, sodium bromate 1 equivalent in acetonitrile water, only secondary alcohol is getting oxidized. So, when there is a primary alcohol, then simple primary alcohol may not be oxidized with CAN. And we will see now which kind of primary alcohols can be oxidized with CAN. So, primary benzylic and allylic alcohols which are more reactive, that can be oxidized with ceric ammonium nitrate. And here one example is benzyl alcohol with ceric ammonium nitrate 10 mole% and tempo 10 mole%. With acetonitrile solvent, it gives 92% yield of benzaldehyde. Again, this alcohol, this is dihydroindanol, this under oxidation with CAN and tempo 10 mole% each in acetonitrile gives this ketone a 94% yield. And this is an example of allylic alcohol. And these two, whatever we discussed, these are benzylic alcohol. So, allylic alcohol also can be oxidized with ceric ammonium nitrate and tempo each 10 mole% in acetonitrile solvent, it gives 94% yield of the product. And now we will discuss the mechanism of oxidation of secondary alcohols using tempo and ceric ammonium nitrate. So, this is the tempo, this tetramethyl piperidine N oxide, there is a radical, this one, and this is also single electron oxidant, and ceric 4 to ceric 3, this is also single electron oxidant. So, what happens, tempo first goes to the N oxide, it gets 1 electron oxidation by cerium, and cerium 4 becomes cerium 3, and this species, this actually oxidize the secondary alcohol to the ketone, and when cerium 4 becomes cerium 3, it again reoxidized to cerium 4 by oxygen. So, this reaction you have to do under oxygen atmosphere, and then oxygen will get reduced to the water. So, this is the whole catalytic system, this is bi-catalytic system, that tempo also is getting cyclized in this reaction, and cerium 4 also getting cyclized in this reaction. So, TEMPO is getting oxidized by cerium and cerium 3 is getting oxidized by oxygen. Another important reaction that ferric ammonium nitrate performs is oxidation of thioethers to sulfoxides, and this thioether with ferric ammonium nitrate, and here again you have to use sodium bromate 1 equivalent, you get this sulfoxide in 99% yield. Both aromatic system and thioether, this also can be oxidized with ferric ammonium nitrate, sodium bromate 1 equivalent in acetonitrile water, it gives 96% yield of this sulfoxide. Also both alkyl group is there, sulfur, this also oxidized, one allyl and methyl group is there under ferric ammonium nitrate 10 mole percent, sodium bromate 1 equivalent and acetonitrile water, it gives 70% yield of the sulfoxide product. Oxidation of epoxides and aziridines, ferric ammonium nitrate also perform this reaction. Here you can see this epoxide is there, styrene epoxide, and it in 0.1 equivalent of ferric ammonium nitrate and 1 equivalent of N-bromosuccinamide. So, this is N-bromosuccinamide, 1 equivalent in acetonitrile water, it gives this 2-hydroxyacetophenone. The alcohol is on the primary and carbonyl is the secondary, this is the ketone. And here also this aziridine, N-tosyl aziridine can be ring open and followed by oxidation with ferric ammonium nitrate NBS in acetonitrile water, it gives this aminoketone in 90% yield. Also a cyclohexyl containing aziridine can be also opened under this condition and gives this aminoketone with cyclohexyl group in 88% yield. So, what is the mechanism of this reaction? And this most likely mechanism that can first hydrolyze the substrate. So, when water is there and ferric ammonium nitrate also is a Lewis acid, cerium 4. So, it will bind to the, it will coordinate with the epoxide, here also aziridine also will coordinate with the cerium plus 4, and then water will attack and will give the water alcohol, and that alcohol will get oxidized with NBS to give the corresponding keto products. So, this intermediate, this reaction intermediate can be considered a diol, and we have already seen that this diol secondary alcohol will be selectively oxidized with this ferric ammonium nitrate. Here also this, here maybe this product, this intermediate will be first form, water attacks from this center here and you get this intermediate, and then after oxidation N-bromosuccinamide you get this aminoketone. Oxidation of alkyl benzenes and active methylene compounds. Under certain condition this ferric ammonium nitrate also oxidized alkyl benzenes, like here ethyl benzene is there, ferric ammonium nitrate 5 mole percent, potassium bromate 0.5 equivalent and dioxin water, you get acetophenone 90% yield. Also when 2-methyl group is there, isopropyl benzene can also under this condition, because there are 2 methyl groups is there and selectively only the tertiary alcohol is formed in 90% yield. Under this condition, ferric ammonium nitrate 5 mole percent, potassium bromate 0.5 equivalent in dioxin water. And diethyl malonate, here also this proton is quite acidic, and under this condition it has been found ferric ammonium nitrate 10 mole percent, oxygen 5 liter per minute, acetic acid acetonitrile solvent, it can give this ketoester product. So, what will be the mechanism of this reaction? So, we can think that first a single electron oxidation will happen, so you get first a radical and again, because this is single electron oxidant, again it becomes formation of a carbocation. And this carbocation under this condition will give alcohol, and when one of the R is hydrogen, then it will be benzyl alcohol, and benzyl alcohol we know that under steric ammonium condition you get the ketone. So, it can further oxidize to this when 1 R is equal to hydrogen. So, if this is a secondary alcohol, then you get the ketone. Now, we will discuss DDQ. This is full name is 2,3-dichloro-5,6-dicyano-1,4-benzoquinone. So, one side 2 chlorine group is there and another side 2 nitrile or cyano group is present. So, it is called 2, 3, 1, 2, 3, 4, 5, 6. 2, 3 dichloro, 5, 6 dicyano, 1, 4 parabenzoquinone or benzoquinone. This is also commercially available. DDQ is very reactive and used under anhydrous condition. So, unlike steric ammonium nitrate is water soluble and you can do even reaction in water, acetonitrile water we have seen. But in DDQ you have to use under anhydrous condition because it decomposes in the presence of water. DDQ poses most modest toxicity and the potential for HCN liberation upon exposure to H2. So, it may be modest toxicity because it can liberate HCN. The reaction is carried out in inert solvents such as benzene, tetrahydrofuran and dioxane. Used as reagent for oxidative couplings and cyclization reaction and dehydrogenation of hydroaromatic compounds and carbonyl compounds. So, hydroaromatic compounds to aromatic compounds and carbonyl to alpha beta unsaturated carbonyl, that we will see in details. So, this compound was first reported in 1906. Thiele and Gunther first reported a 6-step preparation. It can be synthesized from the reaction of benzoquinone with HCN HCl followed by oxidation. So, this is the first step that HCN adds in ethanol H plus condition. You get 2 cyano group from the same side and you get this hydroquinone. Then after oxidation it becomes quinone again and this is HCl actually. So, HCl adds here Cl minus, if Cl minus adds here and then after aromatization you get this hydroquinone and again oxidation to quinone and then again another Cl will come HCl. So, again it will react like this and then after aromatization you get this hydroquinone and oxidation again you get the quinone. So, this is DDQ. So, 2 cyano group in one side and 2 chloro is one side and keto groups are in the para position each other. So, 1,4 parabenzoquinone. This application, it is applied in many reactions. One of them is aromatization. If you have a diaromatic compound, then you can put DDQ, it will aromatize. Dehydrogenation of hydrocarbon, sometimes hydrocarbon has been dehydrogenated to get a double bond. Formation of conjugated double bond, that we will see alpha beta unsaturated carbonyl compound you can generate. Also a double bond conjugated with aromatic system you can generate. Benzylic oxidation, you can, we will discuss that benzylic CH can be oxidized to ketone. Oxidative cyclization reaction also is well known and direct cause dehydrogenative coupling, that is CDC, cross dehydrogenative coupling between benzyl ethers and simple ketones, also other nucleophiles, and direct cross dehydrogenative coupling with tetrahydroisoquinoline. So, this reactions we will discuss. What is the general mechanism, how DDQ operates in the reaction? So, this is generally two-step mechanism containing an initial rate determining transfer of hydride ion followed by a rapid proton transfer leading to hydroquinone formation. So, this is the main reaction that happens actually, that H minus first react, also electron also can react first here, because this is a electrophilic compound, this is parabenzoquinone. So, this electrophilic compound, and then H minus first react here, you get this system, O minus is there, this hydroquinone there is a O minus, and now this O minus is reacting to the H plus, and then you get this motif, and ultimately one H plus and H minus, first H minus and then H plus reacted with the DDQ to get this hydroquinone or DDQH. This we call sometimes DDQH, hydrogenated DDQ. First we will discuss aromatization reaction, and this is tetrahydronaphthalene Tetrahydronaphthalene, if you put DDQ, you generate two double bonds and it get aromatized under benzene reflux condition. Also, if you have this system, this will also aromatize, there will be generate a double bond, and then this compound you can generate under similar condition, benzene reflux. Here, if you put two methylated, one dimethylated tetrahydronaphthalene under DDQ benzene reflux condition, you get this 1,2-dimethyl. So, 1,2 migration of methyl group is observed along with the aromatization. The mechanism we will discuss. And here, if a alpha beta unsaturated ketone is there, then also the aromatization, this group liberates. Because the aromatization is a very facile process, so this group liberates under DDQ dioxane condition, and you get this phenol motif. So, this is very interesting. So, one A will happen here double bond, and then it will be pushing, so that this will leave and you get the aromatization. This is called equilene. Now, we will discuss how this reaction operates. So, as we told that one H minus will first react. So, one H minus, because this is benzylic, so benzylic carbocation is stable. So, H is quite acidic. So, H minus will react, and there will be carbocation formation will be there. So, carbocation formation will be there, and H minus can react either here or here, whatever, it will give the same product. And if it reacts here, and then after tautomerization, you get this compound O minus and H here. So, O minus is generated, and now this O minus will react with one hydrogen here, because this is carbocation. So, this will, like we have seen the olefin formation. So, this H plus will be taken by the O minus, and you get this compound now, neutral compound hydroquinone, and this compound is formed. So, a double bond first generated. Now, again one H minus will react, because this will be allylic carbocation, that is also quite stable. So, H minus will come again to this compound DDQ, and again it will react either here or here, it will generate again a O minus here. And now, this compound, this carbocation, after this carbocation, if you see, this is allylic, but this is a secondary carbocation. And we know that if there is a possibility of a carbocation rearrangement, if the carbocation wants to get stabilized, like from primary to secondary, secondary to tertiary, that process is very facile, and that is what happening here. Here, after 1,2-methyl migration, the carbocation goes to here, and this carbocation, you can see this is a tertiary carbocation as well as benzylic. Tertiary carbocation as well as benzylic. So, this is quite stable. So, this carbocation is stable. So, this 1,2 methyl migration is very facile. You get this carbocation and then this O minus will take up this H plus and you get the olefin, ultimately you get the aromatic compound and your dihydroquinone becomes this, sorry, DDQ becomes this dihydroquinone. Similarly, DDQ performs dehydrogenation of hydrocarbons like this Kroman system. Here 2 methyl groups are there, so it cannot aromatize. So, only one single double bond is formed when DDQ and benzene 80 degree centigrade we do the reaction. Also, cycloheptatriene system, and we know that this is not aromatic, but if you generate a carbocation and this is very quickly possible if you treat with DDQ HCl4 acetic acid, this you get a carbocation and this is aromatic, because this is planar 6 pi electron system. So, this is aromatic and so this process is very facile. Also, if you have a system like this, then also under this condition DDQ sodium nitrate condition you can get the double bond here, and this is also at room temperature you can do this reaction. DDQ also forms conjugated double bond. This is very usual reaction of DDQ, and if you have a possible of conjugation, then it is very facile. Like if you have system like this, diphenyl and intermediate is this, that is the hydrostilbene actually, dihydrostilbene, and then you get the stilbene. So, DDQ generates the stilbene, and this is very interesting that if you have a trans steroid, so these are steroid compound, this we will see the mechanism later also. In a trans system you get dehydrogenation from this side, and in a cis system you get dehydrogenation from the this side. So, this is the geometry of steroid decides regioselectivity of unsaturation or regioselectivity of DDQ oxidation. So, it is the geometry of the steroid. If it is trans, then this side, and cis this side. And also if there is already one unsaturation here, then it does not go this side, in fact it goes to the this side. So, linearly conjugated system, this is linearly conjugated instead of cross conjugated system. So, in this case a linearly conjugated system is generated compared to the cross conjugated system. Formation of conjugated double bonds. So, this is mechanism that we told, the 3 keto steroids are highly dependent on initial steroid geometry. So, when it is trans, then it has been found that this enolate will form, and after this enolate, then you get this hydride elimination for this hydrogen, and you get after elimination of DDQH you get this double bond, alpha beta unsaturated carbonyl system. And in cis system now this enolate is formed, and after that you get oxidation of this one. So, you get this carbon, and when trans case you get this carbon. So, this will be the accessibility, which hydride and H plus is accessible. So, that depending, because here this H minus will react with DDQ and here this also will react with DDQ. So, this is very important, that accessibility of the hydride ion to DDQ, and that is why the facial selectivity operates here. Benzylic oxidation, DDQ also has been found to do benzylic oxidation like this system. In acetone 20 degree centigrade you get 93% yield. This is azulene system, you get the carbonyl here, and it has been used also benzylic deprotection like here simple benzyl group is there, but here activated 3,4 dimethoxy system is there, and when DDQ in dichloromethane aqueous dichloromethane was treated with this substrate, you get deprotection and you get this allylic alcohol. So, this benzyl group still remains. So, this is very important. This group is more electron rich. So, it has a chance to more react with the DDQ. Oxidative cyclization, DDQ also used in oxidative cyclization reaction. If you see this compound, there is a benzyl carbon here, and with DDQ condition you get the cyclization. So, what is happening? This is a carbocation, that is what we told earlier with ferric ammonium nitrate. Here also you get a carbocation, and this is reacting with the carboxylic acid, maybe the anion of the carboxylic acid, and you get this compound, because this is 6 member ring formation. So, this is quite facile. When you have a olefin here and then also the 5 member ring will form, so most likely this goes via this carbocation. So, this electron reacts with DDQ and then generate a carbocation here, and then it is reacting, and then after dehydrogenation, because DDQ also do the dehydrogenation, and then you get this aromatic system. And this compound, it has been found that when it cyclizes, then the double bond isomerized, and you get this 6 member ring. So, here also first this carbocation will form, and then it will go to this compound, and then as we have seen that DDQ dehydrogenate. So, this product or intermediate will be converted to this product. So, the cyclization will happen because this electron cloud will react with DDQ to generate a carbocation, and then cyclization, and then again dehydrogenation will give this compound. Direct cross dehydrogenative coupling between benzyl ethers and simple ketones. This is benzyl ethers, and ketones, it can give this reaction. So, alpha position of ketone, because the electrolyte formation happens, and then it reacts to the oxonium ion. So, detailed mechanism we will see, and this condition is DDQ 100 degree centigrade. Suppose if you do this reaction chroman and 2-butanone in 3 equivalent, and DDQ, this is anhydrous condition 100 degree centigrade, nitrogen atmosphere 2.5 hours isolated at 50%, you get a mixture of product. So, ketone 2 positions are there, this is primary, this is secondary. Here it has been found the secondary, that product is more in 1.5, and this is 1 ratio. But main thing is that CC bond formation happens. So, that is why this is called also cross dehydrogenative coupling. Other nucleophiles can also be used in this reaction to the chroman, and like dimethyl malonate can be reacted with chroman. You have to use other Lewis acid along with DDQ. In room temperature you get 77% yield of this product. So, here also you get a oxonium ion, and then this negative charge of dimethyl malonate, this react here, and you get this product. Here also this is activated nucleophile nitroesters, and this nitroester under this condition indium chloride copper triplet which acts as Lewis acid, and DDQ, you get these products in DR is 2.5:1. Not only benzylic ethers, allyl ethers also can be reacted under this condition. So, DDQ, you have to use lithium chloride here, DDQ, lithium chloride and dichloromethane is solvent, you can get the carbocation first, then the oxonium. So, this is the oxonium ion, and then a nucleophile can be reacted. As you can see, this is the allylic ethers, this is the formation of carbocation here, and this hydride will be taken by DDQ, and DDQ then the oxonium ion will generate, and you get a reaction with TMS cyanide, you get 82% yield. Similarly, enol ether, OTMS silyl enol ether can react to give this ketone. Similarly, allyl nucleophile, allyl tin nucleophile can be reacted with this allyl ether to get this product in 79% yield. Similarly, if there is a branch also, the reaction is possible. So, the branching does not affect the oxonium ion formation, and you get 94% yield. Also, if this is a OT base, not only methyl, this is all methyl, here OT base, this is also possible. So, the silyl does not affect the oxonium ion formation here, and you get the oxonium and then cyanide. However, the yield gets reduced. So, methyl ether are better choices compared to the silyl ethers. Direct cross-degenerative coupling between benzyl ethers and simple ketones. So, this is the mechanism that benzylic ether, this oxygen, there is a lone pair, and we can think that first one electron goes from the oxygen lone pair to this DDQ, and you get a radical here, because if you see this structure, and the electron, if it comes here, then single electron, then a radical will form here, O radical and O minus here. So, this will be radical. And what happens now, again this H dot will go to this O dot, and it will give the OH, and because there are two radical, now this bond will form. So, oxonium ion will form, and you get the anion. Now, this is goes to OH, and this you get CN CN Cl Cl, and this O minus then reacts with the ketone. So, this O minus reacts with the ketone to generate the enolate, and this already is oxonium ion. So, what happened? DDQ activating both electrophile and nucleophile, both partner, this as well as the carbonyl compound, this both activated by DDQ. So, this enolate is forming, because this is the base now, and after deprotonation it becomes the hydroquinone system, and now this is a oxonium ion, this is a enolate. So, this reaction will take place, desired reaction, and you get the CC bond formation. Activation of tetrahydroisoquinoline, not only chroman, but quinoline system also, isoquinoline system can also be reacted under DDQ. So, DDQ nitromethane solvent room temperature, if you have the N-phenyl system, you can get reaction with nitromethane. So, CC bond formation. Here also mechanism most likely iminium ion is formed. So, first one electron, then another electron oxidation, and then you can get the iminium ion. And it has been seen, it has been observed this, that the iminium ion is forming, actually that also can be observed by changing the changing the R group. Suppose when hydrogen is there 95%, methoxy 95%, 80%, and when R is equal to NO2, then you get 58%. So, if there is a electron withdrawing group, then the iminium ion is destabilized. And this is a chiral version with steric ammonium nitrate and with chiral ligand and palladium catalyst. So, this is the phosphine ligand and palladium triplet is there, and under this condition with Bock anhydride and diisopropyl malonate is acting as a nucleophile, and you get this product. Here the Bock group is required, otherwise this reaction will be reversible. So, if you put the Bock anhydride under this condition, Bock protection is happening and you get this product in 86% enantiomeric excess. So, this is very important that steric ammonium nitrate can generate the iminium ion, and then the chiral catalyst will do the facial selectivity, so that the one phase is blocked of the iminium ion, and you can get the addition from a selective one phase to get a chiral or enantiomerically enriched product. Now, we will discuss another oxidizing agent, which is selenium dioxide. So, this is selenium dioxide, selenium is 4. We know that oxygen, sulfur, selenium, it is in the that series. So, it is colorless crystalline solid. It is soluble in solvents like dioxane, ethanol, acetic acid and acetic anhydride. It is extremely poisonous and should be carefully handled while working with it. It is very selective oxidant. It exists as one dimensional polymeric chain with alternating selenium and oxygen atoms. Compounds of selenium are very poisonous and smelly. So, you have to handle carefully. Selenium dioxide, one major application is the allylic oxidation. Like this allylic system, there are 3 allylic carbon is there, this methyl and this CH2 group, and if you put selenium dioxide in ethanol, you get selectively this methyl is going to the CH2OH group. So, this is very important. So, the group which is getting oxidized, which is trans to this group. So, what means? It means that it is sterically more accessible. So, the methyl group which is more sterically accessible is getting oxidized to the OH. This methyl is getting oxidized to the allylic alcohol. And here also you can see this is geranyl acetate, selenium dioxide, here it is catalytic amount, and tertiary butyl hydroperoxide, it is the stoichiometric amount in dichloromethane solvent. There are many allylic carbon, this. So, selectively only one allylic carbon is getting oxidized with selenium dioxide, that is the this methyl group, which is also trans to this is trans to each other. That means sterically which is more accessible, that is sterically less hindered, that carbon atom will get oxidized. And here you can see only one allylic carbon is there. So, that is why tertiary alcohol is generated here. So, when there is no other opportunity, only one carbon is allylic, that case only one product will form. So, you get this tertiary alcohol under selenium dioxide catalytic amount and tertiary butyl hydroperoxide stoichiometric amount. Here cyclohexene is used and cyclohexenol is formed. You can see 0.1 mole of selenium dioxide and tertiary butyl hydroperoxide. This is the mechanism of this allylic oxidation. So, what happens, this allylic CH, that is what, this CH which is more accessible, this reacts with this oxygen here, and now this double bond is migrates. So, this is in kind of reaction and you get reaction here, and this hydrogen is this hydrogen. So, this hydrogen is going to here with the oxygen and you get selenium carbon bond here, and which is not very stable. So, that is why again 2,3 sigmatopic rearrangement is happen. So, this is allylic selenic acid less stable. Now, again oxygen is reacting here and you get this carbon silicon bond breakage and you get this compound. And this compound, if you hydrolyze, what will happen? This bond will break and you get ACOH, ACOH. So, this becomes 2. So, selenium 4 becomes 2 and you get the allylic alcohol. So, 2 times rearrangement of the double bond keeps the double bond in the same place. First in the in reaction and 2,3 sigmatopic rearrangement. Oxidation of carbonyl compounds, which is relay oxidation also called. SiO2 oxidizes active methylene or methyl group present adjacent to the carbonyl group to give 1,2 dicarbonyl compound. This is also very popular reaction of selenium dioxide. As you can see here, acetone with selenium dioxide efflux condition gives this ketoaldehyde, and this is an intermediate for hemizaran B. Mehta group did this reaction and selectively this carbon is getting, because this is the alpha to the carbonyl. Under this condition, selenium dioxide acetic acid catalyst H2 dioxide reflux, you get this 1,2 keto system, which is an intermediate for hemizaran B synthesis. Also, acetophenone can be reacted with this selenium dioxide ethanol, you get the ketoaldehyde, that is the alpha to the carbonyl going to the carbonyl group. And here there is no carbonyl group, only the A is there, but this is unreacted. Only under this condition this allylic goes to the first alcohol and then it goes to the aldehyde. So, what is the possible mechanism for this reaction? So, here also this hydrogen will react. This hydrogen is acidic and this will react to the oxygen. It will go to the oxygen to make a OH, and this selenium will make a bond here with the carbonyl group. So, you get this in reaction, this is also in reaction, that selenium reacts with the carbonyl and hydrogen goes to the oxygen, and you get a oxygen silicon bond. Again 2,3 sigmatopic rearrangement. 2,3 sigmatopic rearrangement generate this one. This oxygen now react here and you get O silicon bond breakage. So, this bond is breakage to make another O silicon bond. So, earlier what we have seen, that this kind of system, if you give the water or the water present in the solvent hydrolyzes this bond. But in this case what is found, that this proton, this is quite acidic because this is alpha 2 carbonyl. So, this is quite acidic enough. This is quite acidic enough to get eliminate, and you generate this carbonyl here and this oxygen silicon bond breaks like this. So, you get a carbonyl group here, carbonyl group is generated. Not only earlier what we have seen the allylic alcohol generation, only this bond breaks, but here this hydrogen is acidic enough, so that rearrangement happens, that the carbonyl is generated and you get H2 and selenium. Instead of ACOH, here selenium 0 is formed. So, allylic oxidation we have seen ACOH whole 2 is forming, but here selenium 0 is forming. Selenium dioxide also has been used to oxidation of alkynes, like this compound is converted to benzyl in selenium dioxide H2SO4. Also phenylacetylene is converted in selenium dioxide H2SO4 to the ketocarboxylic acid. Benzylic oxidation can also be performed with selenium dioxide, only you need very high temperature. So, 200 to 210 degrees centigrade. Under this condition you can oxidize the benzylic group. We have seen that in DDQ condition, even in CAN also, but here selenium dioxide can also oxidize benzylic carbon to a keto group. So, here benzophenone is forming, and here this methyl group is getting oxidized to the aldehyde group with selenium dioxide condition. So, another reagent that has been used which is phenyl selenium bromide, this is preparation of alpha beta unsaturated carbonyl compounds. So, if you have a ketone, then with a base and phenyl selenium bromide you get the alpha functionalization of alpha selenium compound, and then with H2O2 you get the alpha beta unsaturation here. So, this reaction also is popular and it has been used in many natural product synthesis. Here is one of the complex molecule with a carbonyl compound, and when it was treated with phenyl selenium chloride you get this carbon selenium bond, and this when treated with H2O2 it becomes alpha beta unsaturated carbonyl. So, we will discuss the mechanism here. As you can see, first base generates at enolate, then enolate reacts with phenyl selenium bromide to get this alpha selenium ketone, and then oxidation happens of selenium to get the selenium oxide here, and then the elimination happens of the carbon selenium bond breaks, and under this condition you get the olefin, and what byproduct is ACOH-PH. So, this is the byproduct of this reaction. So, today we have discussed three oxidizing reagents. First one was the steric ammonium nitrate. We have seen steric ammonium nitrate oxidize secondary alcohol compared to primary alcohols. It also opened aziridine oxidative reaction, that amino ketone you can get, also epoxide also it opened and you can get the keto alcohol, also benzylic carbon also can be oxidized. And with DDQ mainly does the unsaturation. We have seen it helps in aromatization, alpha beta unsaturated carbonyl compound. Also cross dehydrogenative coupling also it has been used. It has been used to activate cumin, also tetrahydroisoquinoline. Also we have seen that oxidative cyclization reaction also it has done, and you can get, if a phenolic oxygen is there, then it can do the cyclization. And now selenium dioxide very popular for activating allylic methyl group, and the methyl group which is more accessible, less sterically crowded, generally trans to a carbon atom, that methyl group selectively oxidize with selenium dioxide to alcohol. And when a carbonyl compound is there, then also selenium dioxide, this is special of selenium dioxide, it can give 1,2 dicarbonyl compound. Thank you.